Hello and welcome. Right now we're going to be doing problem 669. So this is another frame and machine problem. And we can see right away that this looks like we've got three members to this system with different loads being applied to them. So we should be able to recognize right away this is going to be a frame and machine problem because there are these distinct bodies that are connected at these various spots. So I guess a couple things that we're going to notice right away is first of all, we've got distributed loads. So we need to make sure that we know how to handle those. Um, in order to determine our reactions at each of these, we're going to be replacing our distributed load instead by a resultant force that is equal to the area under each distributed load. We can see this is asking us to determine the reactions that supports A and B. And so here at A, we've got this member that is just attached to the wall. So this is a fixed end. And then we can see at B, this is attached by a pin. And so by now we'll know the different reaction forces that will be present at each of those ends. Something else that's really important, this is not really that important. If you don't notice it, it's not that big of a deal, but we can kind of save a step here if we notice something. And so take a second to look at this image and see if there's anything that looks familiar here that might be able to help us in our process. And so hopefully you're noticing that this member CD is a thin member with only pin reactions at either end, which means that we can treat CD as a two-force member. That means that the force at C and the force at D both have to be in line with this member. So we don't have to actually draw this as one of our bodies. We're just going to, at point C on our first body, make sure that our force is drawn in line with this member. And then similarly at D, it's a two force member. We know the direction of that force. And yeah, we know the direction of that force. So we'll be able to just add that in. The other thing that we can see here, and I'll point this out while we have the full diagram, if we're looking at the dimensions, this x coordinate for CD is 8 feet, and the y coordinate is 6 feet. And so if we divide those numbers by 2, then we're going to have 4 feet and 3 feet, which means this is going to be 5 feet. So this is actually a 3, 4, 5 triangle. And so sometimes we just need to pay attention to what these numbers are and check to see whether or not they're in a ratio for 3, 4, 5 triangle. And in this case, they are for C and D. And so we'll be able to add that angle from our two force member acting at C from a 3, 4, 5 triangle. So I'll flip over to my page. And I've got my setup steps written down here already. First one, disassemble and draw component parts. These are the free body diagrams. And then we'll do our equations of equilibrium. And we're going to make sure that we start with a body that has 3 or less unknowns and 1 or more known. So the first step here, and maybe I'm even going to make a note right away. What do we notice about member CD? That this is a two force member. And so I just want to have that explicitly written on my page for when I skip that step or skip that body. Okay, I'm going to draw my free body diagrams now. I'll start with, and I can label this AC, or I can label it a number. Doesn't really matter. I'm labeling it twice, but you can use whichever convention that you're comfortable with. And I'm going to draw my free body diagram here. So here is my member. There's a distributed load. And so whenever I'm drawing my free body diagrams with my distributed loads, I like to draw just the shape. So in this case, I'm just going to draw the triangle. And then I'm going to draw where that resultant force is going to be located. And so we've got a triangle here that is the same on either sides, which means that that resultant force is going to be right in the middle of this triangle. This, where this resultant force, FR, is going to be equal to the area that's in under this triangle. And so let's double back here, and we see that the peak, the height of this distributed load is 500 pounds per feet. So that's the height. And then the base is 6 plus 6 is 12. So the area of a triangle is half base times height. So we have 1/2 base times height is going to be equal to 1/2. The base is 12 feet. The height is 500 pounds per foot, put to the -1. This is going to be equal to 3,000 pounds. So now I've just replaced this distributed load with a resultant force that acts through the centroid of that triangle. Okay, we're going to keep going here. I'll add some dimensions in here. We know that this is 6 feet on either side. Like that. Now, this is where we're going to deal with this two-force member CD. And I should probably label these different sides. We have A over here. We have C over here. And so here we've got this force FCD. And I don't know how this is accurate, but I'm just going to assume that it's pushing against this member, which means this FCD is in compression if it's pushing against. And this is also a 3, 4, 5 triangle. And then the last thing is we need our reactions at A. This is a fixed member, which means it's going to have a Y component, AY. It's going to have an X component, AX. And because it's a fixed end, it's also going to have a reaction moment, MA. So here's our first free body diagram. And so now let's draw DB over here. So DB. DB. And so I'm going to handle this two-force member right away. So this FCD is pushing against point C. That means it's going to be in compression. And again, I'm not sure that it's in compression. I'm just making that assumption as I'm drawing it. So therefore, I'm going to draw it the exact same way, pushing against point D. And so really, I just want to make sure that I'm drawing these arrows parallel and opposite. That one's a little bit longer, which I don't like, but I'm going to live with it. So we have FCD. Again, this is a 3, 4, 5 triangle. So we've drawn that same force on both of these. Now, if you wanted to, if you didn't recognize this, you could just draw the CD member and you would just have a 2-force member with the same force acting at each of those. You're going to end up with the exact same result. Okay. Now we've also got a distributed load. That's going to act like this. Now, a couple things here. The first part is where are we going to put this resultant force? This other one here, we know it goes in the middle. It's the same on both sides. We're going to put it right in the middle. This one is not that. This is not the case. And so our centroid is going to be located 1/3 from the base. And so the way this is right now, this is the base, but we can tip our triangle like this, such that our centroid is going to be located somewhere like this, where this distance here is going to be 1/3, or just 1/3, whatever this total distance is. And so then our resultant force is going to go through this point. And so let's check what this distance is. This distance is 9 feet from DB. So if this is 9 feet, that means that this distance is going to be 3 feet. And then this side over here is going to be 6 feet. So this 1/3 triangle thing, if you're finding this confusing, I will link to, I've done a demo, a separate video that is a demo of how we get to that 1/3 from each of the different sides. And so we just need to know that such that we can plot where that force acts on this, or where this resultant force acts. So this is our resultant force over here. Our resultant force, same thing as over here, is going to be equal to 1/2 base times height. In this case, the base is 9 feet. Our height is 700 pounds per foot. This is going to be 3,150 pounds. And this is a pin at B. Since this is a pin, this means we're going to have a Y component, BY, and we're going to have an X component. BX. Okay, so we've drawn both of our free body diagrams. On this side, we can count up here. We've got one known. We know this is 3,000 pounds. So we have one known, and then we have AX, AY, moment at A, and FCD. So we have 4 unknown. And so that's a concern. We know we need 3 or less. we need 3 or less, so we're concerned about that. So let's look over here on this other side. We've got our resultant force 3150, so we have one known. And if we count our unknowns, we've got FCD, BX, BY, which means we have 3 unknown. So we're going to start here. And I just realized that I did not label this one. So this is DB, or we can call it body 2. So we're going to start with this. We're going to start with this side. So over here, DB, also write body 2, whichever one we want to call it. So we need to solve for all 3 of these forces. And we can kind of see here, we're going to start at this one. We're going to basically, we need to solve to see what FCD is. And then FCD is going to give us 2 knowns and 3 unknowns for our next body. So then we'll be able to work our way through. So we'll start here, solve for these, move over, and then we'll solve for these ones. Okay, so the first thing we can do, we can sum our moments about B to solve for FCD in one step. So let's do that. I'm going to sum our moments about B are equal to 0. We have 3150 pounds times 6 feet minus 3/5 FCD times 9 feet equals 0. We'll solve this to get FCD is equal to 3,500 pounds. Now, if all we needed to do was solve for our reactions at A, we could then step over and then move to AC and solve right away. But the question says solve for the reactions at A and B, so we still have to solve for BX and BY. So let's do sum of forces in the X equals 0. We have, whoops, that should be 4/5. In our X, we've got 4/5 in our X, not 3/5. 4/5 times 3,500 pounds minus BX equals 0. BX is 2,800 pounds. Now we'll keep going. Sum of forces in the Y equals 0. Three over 5, which is times FCD, which is 3,500 pounds, plus BY minus our distributed load of 3,150 pounds equals 0. BY is 1,050 pounds. Right, so we've solved for 2 of these. So now we can keep going. Make sure that we can still see the free body diagram for AC, at least while we get it started. AC body 1. And so if we know FCD, which we're bringing over from the other one, if we look in the X, the only components here that are in the X are FCD and AX. So we can solve for AX right away. So sum of forces in the X equals 0. We have AX minus 4/5 times 3,500 pounds equals 0. AX is 2,800 pounds. Now we can look at, it's the same thing with AY. We've got 3 components in the Y, but now we know 2 of them, and we just need to solve for AY. So we'll sum forces in the Y equals 0. AY minus our distributed load, which is 3,000 pounds, minus 3/5 times 3,500 pounds equals 0. This gives AY is 5,100 pounds. This up a little bit so we can still see. Then the last one here, we just need to solve for our moment at A. And so in this case, we'll sum our moments at A and just include that moment at A from our fixed reaction. So sum of moments about A is equal to 0. We're going to have our moment at A from the wall. Start with that. Minus 3,000 pounds times 6 feet minus 3/5 times 3,500 pounds times 12 feet equals 0. We can solve this out. Moment A is equal to 43,200 foot-pounds, or 43.2 kilopound feet. And so maybe just a short aside, one thing with American units that it's kind of strange is if we often refer to it as foot-pounds. So we've got our distance times our force, but then once we add this kilo prefix, we then change it to kilopound feet. It doesn't really matter. Either way, we just need to know that this is times 10 to the 3 because we have our prefix here for kilo. So there you have it, another frame and machine problem. Again, if you're confused about this 1/3 distance to our distributed load, this needs to act through our centroid. We're replacing that force with a single force. And watch that other video that just shows that demo of how we come up with that. At least how it works from all 3 different sizes. So that's it for this problem.